Chapter 6, Representing Molecules. This presentation will cover the octet rule, covalent bonding, electronegativity, polarity, and dipole moments. The second half of Chapter 6 on drawing Lewis structures will come in the next presentation. The general statement of the octet rule is that it signifies the observation that atoms of the main group or representative elements tend to gain, lose, or share electrons in order to have the same electronic configuration as a noble gas. This information is very useful for monatomic ions. However, we will find that as we proceed down the periodic table and look at covalent bonds, that the octet rule may not be as useful as we think. The octet rule for covalent bonds basically is a useful tool for building the skeleton of Lewis structures. However, a more useful rule to keep in mind is the total number of electrons that can occupy a given shell. That is, all the orbitals within the same principal quantum number. Looking at the table below, in n equals 1, the first row of the periodic table, the total number of electrons that can be held is 2. As a result, only one bond can be formed, as we see with hydrogen. In period 2, there are s and p orbitals. The total number of electrons is 8. This is the octet rule. This gives us 4 total bonds that can be used. So as we can see, the octet rule will apply very well to compounds boron, carbon, nitrogen, oxygen, and fluorine. In period 3, we have 3 subshells, the S, P, and D, for a total of 18 electrons. 18 electrons equates to 9 total bonds, and what we will find is that elements like phosphorus, sulfur, chlorine, and even going further down the periodic table, selenium, bromine, iodine. Also, we can include elements from the noble gases such as krypton and xenon will bond more than 4. That is, they will not have an octet. They will have something more than an octet. Using the information from the previous slide, in covalent bonds, the octet rule is useful most of the time for elements in periods 1 and 2 as indicated. Looking at water here, hydrogen is a period 1 element and can have a maximum of 2 electrons in its bond, and as you can see here on the left and on the right, if we circle hydrogen, there are 2 electrons in its outer shell as a result of sharing with the oxygen. This results in a single bond. For the oxygen, the sharing of electrons with the hydrogens gives it an octet. It's a period 2 element, can have a maximum of 8 electrons in its outer shell. Similarly, fluorine over here in sulfur hexafluoride will have 8 total electrons in its valence shell, 2 from the bond here, and then 6, these lone electrons out here, for a total of 8. However, looking at the sulfur, we see that it has surrounding it 6 bonds. 1, 2, 3, 4, 5, 6. With 2 electrons in each bond, that's a total of 12 electrons. Being in the third period of the periodic table, as previously indicated, the sulfur can have up to 18 total electrons in its valence shell. It doesn't have to have 18, but it can hold definitely more than 8 according to the octet rule. Single bonds between atoms is the sharing of a single pair of electrons. Usually each element in the bond or each atom in the bond contributes 1 electron. This is not always the case, but it is the usual case. In designating this in a Lewis structure, we can either designate it as the 2 dots or as a dash. The dash is less cluttered and is more often used. Double bonds represent the sharing of 2 pairs of electrons between atoms. Again, generally each atom in the bond will share 2 electrons for a total of 4, that is 2 pairs. Using a double dash like this helps us to condense the structure and have a less cluttered look. A triple bond is the sharing of 3 pairs of electrons, or 6 total electrons, generally 3 from each atom. And the line designation is 3 parallel lines. Amongst the nonmetals, generally there are single, double, and triple bonds. Quadruple and higher order bonds generally don't exist amongst the nonmetals. However, they will occur in some of the metals as they bond with each other. The next topic is electronegativity. Electronegativity is not like electron affinity, which we can measure, or ionization energy, which we can measure. Electronegativity is the ability of an atom to attract toward itself the electrons in a chemical bond. It is generally a more qualitative measure. However, it is very useful in helping us determine polarity of a bond and polarity of a molecule. Here is the electronegativity table, and as you can see, starting down here with francium, the electronegativity goes up as you go toward the top of the periodic table, and then also increases as you go to the right on the periodic table. Notice that helium, neon, and argon do not have electronegativities because they don't form bonds. However, krypton and xenon do have electronegativities because there are known compounds of krypton and xenon. Even though we call them noble or inert gases, krypton and xenon can be made to form bonds, especially with oxygen and fluorine and sometimes chlorine. Note here that at the very low end are the alkali and the alkaline earth metals. In the intermediate zone here, most of the transition metals are in the intermediate area between 1 and 2 on the electronegativity scale. There are a few of the transition metals that are a little above 2. Hydrogen is at 2.1, and then the majority of the nonmetals are between 2 and 2.9. There are 4 elements at 3 or above: nitrogen and oxygen, chlorine, and krypton. And then finally at the top end is fluorine. It gets the 4.0. The usefulness of electronegativity is to see the difference and to estimate the quality or quantity of the electron transfer in the process. When their difference is 0, there's basically equal sharing. And as that difference gets larger, for example, in hydrogen fluoride, the difference is 1.9, there's unequal sharing of the electrons. The hydrogen end down here on the blue is blue because it has less of the electron density, and the red end is the higher end. It has more of the electron density on the fluorine. As a result, there is a polarity that has occurred from this unequal sharing. When the unequal sharing gets extremely large, for example, between sodium and fluorine, basically the electrons in the sodium here have been completely transferred, the one electron from its outer shell, to the fluorine over here, creating an ionic compound. We would be classifying bonds between atoms based upon their electronegativity difference. The calculation is taking the larger electronegativity and subtracting the smaller electronegativity. If you get a negative number, just take the absolute value of that number and compare it to this chart. If the difference is less than or equal to 0.4, then we're going to call that a covalent bond or a non-polar covalent bond. When we get to 0.5 and up to and including 1.8 in our difference, those are polar covalent with increasing polarity as the difference gets larger. At 1.9 and up to 2.2, we will designate these compounds as being partially ionic because many of them exhibit ionic characteristics, especially in aqueous solutions. And then finally, as we go above 2.2, these compounds, a great many of them, tend to be ionic in nature. So we will call those types of bonds ionic. We will classify the following bonds. First, we're going to look at the cesium chloride, the bond. Cesium has an electronegativity of 0.7. Chlorine has an electronegativity of 3.0. The difference is 2.3. This is an ionic bond. In hydrogen sulfide, the hydrogen has an electronegativity of 2.1 and the sulfur electronegativity of 2.5. The difference there being 0.4. This is at the upper end of the covalent range, so this is a covalent bond. Next, the nitrogen-nitrogen bond in H2NNH2, which is called hydrazine, is designated as a covalent bond, which is easy to figure out because each nitrogen has the same electronegativity and their difference would expected to be 0. And finally, the bond in hydrogen fluoride, we've seen this one before, but to put it on this so we can see the numbers and classification, hydrogen is 2.1, fluorine is 4.0, the difference is 1.9, the beginning of the range that I call partially ionic. And finally, we're going to look at dipole moments and polar bonding. In a compound such as hydrogen fluoride, there is an electron poor region and an electron rich region. This creates a separation, or is created by a separation of charge, and we designate that separation of charge by using partial positive and partial negative designations with the delta symbol, or we use an arrow with the positive at the electron poor region and the arrowhead at the electron rich region. It's not until we get to the high differences and we get complete transfer that we get full charges that we would see, let's say, in sodium fluoride, where the sodium is +1 and the fluoride is F-.